Okay, well, welcome to the NISS-CANSSI Collaborative Data Science webinar. Thank you to the National Institute of Statistical Sciences and the Canadian Statistical Sciences Institute for sponsoring this web series. The goal of this series is to showcase experts from various fields who tackle complex data challenges through interdisciplinary teamwork. And we do that by featuring collaborators, a pair of speakers, one from data science and one from an area of science, speaking about their problem together. I'm Nancy McMillan. I'm the moderator for today. I'm a data science research leader at Battelle Memorial Institute, and I'm a member of the organizing committee for this web series. If you have ideas for this web series, maybe even yourself, please feel free to reach out to an email address that I will put in the chat once we go live. I don't want to make you write it down. This is our last event of our spring series. We're going to pick back up in September after this. We have Dr. Lauren Cowan and Dr. Patrick O'Hare talking September 18th when we restart in the fall. Dr. Cowan is professor of mathematics and statistics and the acting dean of science at the University of Victoria. And they're going to be talking about a marine application. Her co-speaker, Dr. Patrick O'Hare, is at Integrated Marine Spatial Ecology Lab at the Institute of Ocean Sciences. So that'll be in the fall. Our topic for today, though, is data science techniques for control of assistive devices after neurological injury. Sorry about that. Our speakers are Dr. Lauren Wengerd, Assistant Professor, Department of Neurological Surgery at The Ohio State University, and jointly appointed to the NeuroTech Institute. With a clinical background in occupational therapy and a PhD in health and rehabilitation sciences, she leads interdisciplinary research at the intersection of neurorehabilitation, neurotechnology, and patient-centered care. She received her PhD from The Ohio State University in health and rehabilitation sciences and an MS in occupational therapy from the Medical University of South Carolina. She also has a BS in business administration from The Ohio State University. Dr. Friedenberg, our statistician speaker, is a principal data science and neurotechnology and team lead for machine learning AI and the advanced analytics group at Battelle, also at Battelle Memorial Institute, like me. He's the PI on several neurotechnology efforts, developing new AI-powered technologies to help improve the lives of people living with motor impairments due to neurological injuries like spinal cord injuries and stroke. Dr. Friedenberg received his PhD in statistics and his MS in statistics from Carnegie Mellon University and started with a BS in mathematics and statistics at Miami University. So if you have questions during this presentation, put them in the Q&A. I'm going to hold them and ask the speakers those questions between slides. I won't hold them for very long. And with that, I'll turn it over to, excuse me, I'm not sure who's starting, Dr. Wengerd and Dr. Friedenberg.
Great. Thank you so much, Nancy. And thank you to NISS for inviting us. We are happy to be here. Again, Nancy did a wonderful job introducing us. So this is just a brief background. I'm an occupational therapist clinically and an assistant professor at Ohio State, and collaborate often with Dave Friedenberg, who's a senior data scientist at Battelle. So before we get into the projects that we're working on, we did want to give just a brief overview of the patient population that we're going to be talking about today. So first we'll start with stroke. So stroke in the United States is one of the conditions that we are targeting with the technology we're going to discuss. It's a very common condition. There's about 795,000 new strokes per year and over 6.5 million people living with the results of stroke in the US. And that number is going up for good reasons, in the sense that we are better able to manage stroke now than we used to be. Oftentimes people didn't survive strokes. Now more and more people are surviving strokes, but they're left with, upper extremity and lower extremity paralysis that limits their independence with daily activities. So that's one of the issues that we're trying to tackle. And 2 out of 3 stroke survivors require rehabilitation. And so what that looks like for us, the devices we're talking about today are largely related to what we're going to refer to as the upper extremity, which is the arm and the hand. And after a stroke, it's called hemiplegia or hemiparesis. They're kind of used interchangeably. And that essentially just means that there's weakness or paralysis on one side of the body. And so anyone in this group that's maybe seen someone who's had a stroke, you may notice that their hand and wrist look like these pictures where they get kind of tight and fisted, and they aren't able to move in a nice fluid way that the rest of us are. It is the most common post-stroke deficit, in addition to things like language impairment, impaired gait, things like that. But we are specifically focusing our technologies right now largely on upper extremity recovery. And like I mentioned, I'm an occupational therapist. So our role, we work closely with physical therapy and speech therapy. And we often address upper extremity deficits, but also anything that limits people's independence with daily activities. So if they have trouble dressing themselves, bathing, driving a car, preparing meals, anything like that, they're likely going to have an occupational therapist or an OT. And stroke is the most common diagnosis seen by OT, which is why it's of particular importance to us. And the current standard of care, so what we normally do in OT rehab, you can see some pictures here. We train patients on different types of adaptive equipment, how to do things one-handed. We also do what's called task-oriented training, meaning we want them to get a lot of repetitions of just attempting to use that hand and arm for, grasping and releasing objects. And then we combine that with open loop functional electrical stimulation, which we'll get to here in just a minute. I'll go into more detail on what that looks like. And then the other condition we're going to talk about today is spinal cord injury. So just briefly, spinal cord injury is not as common as stroke. There's about 18,000 new spinal cord injuries per year in the US, and about 300,000 people living with spinal cord injury in the US. While the pie, I guess, or the number of spinal cord injuries is smaller than the number of strokes, the number of people with a spinal cord injury who require rehab and who have really severe deficits is much larger. So that's another reason that we're really targeting this. Over 50% of spinal cord injuries result in what's called quadriplegia, which is, it involves the hands and the legs, or, it starts somewhere in their cervical region or their neck region. And so again, we're using the technology we're going to talk about today to try and treat some of that upper extremity impairment that they experience after a spinal cord injury. So briefly, just these are some types of paralysis that you may see or that we may talk about today. So I mentioned hemiparesis or hemiplegia. That's where half of the body is impaired due to like a stroke in the brain, causing the opposite side of the body to have motor and sensory impairment. And then spinal cord injuries often lead to either quadriplegia or paraplegia. So the red denotes what's usually impaired. Paraplegia means that it happened in the thoracic or sacral region or lumbar region. So it's going to result more in like lower extremity impairment, but their hands and arms are fine. And quadriplegia is what we're targeting, which is like upper and lower extremity. And then there's also monoplegia and diplegia. These are usually due to things like post-polio syndrome, multiple sclerosis, or cerebral palsy. So those won't be the focus of our talk today. And briefly, before we show you the technology, I wanted to show you what traditional functional electrical stimulation looks like. So what we do oftentimes is we put these sticky back electrodes on. So you can see the therapist applying the electrodes to the patient. And then those will be hooked into a system that's just stationary, sitting on a base. And she can place the electrodes wherever, she feels like the patient needs them. And then on the right, this is just an image of what that therapy is going to look like. So now he's all hooked up. She has plugged the electrodes into the system. And what you can't hear in this video is because it's open loop, he's not controlling the stimulation. So it's like essentially dinging. It'll ding, and that tells him, okay, now we're going to stimulate the muscles that open your hand. So it's trying to open his hand for him. And he's supposed to move along with it and try to open his hand as well. But there's no way to know if he is or isn't because there's no EMG control in this system. So traditional FES systems, the big takeaway here is they're open loop, so they're unidirectional, and they just stimulate the muscles without having feedback from the patient. And so what we're trying to do with our technology is closed loop FES or functional electrical stimulation. And so before an injury, this is what a normal motor and sensory feedback looks like. You have really strong motor output from the brain, and that creates a strong EMG signal, which results in normal movement. And then because of that normal movement, you get normal sensory or strong sensory feedback that goes back to the brain, and you have this nice loop of control. What happens after a stroke is the damage leads to weak motor output. So your EMG signal gets smaller and a little bit more murky, for lack of a better word, which leads to weak motor activation and then weaker sensory feedback. And that's ultimately is what causes impaired movement. And so we're trying to intervene by taking that EMG signal, decoding the residual motor output that we're able to detect using our high density EMG, and then stimulating the muscles to control movement in a functional and intentional way. So unlike traditional systems that are, it dings, it turns on, and it stimulates the muscles to open or close the hand, this is actually giving the patient back the control where they're controlling it themselves. It's using their own EMG. When they attempt to open their hand, it stimulates, and when they close their hand, it turns off. I'm going to pass it over to Dave, who's going to talk about our technology.
Thanks, Lauren. So the way that we do this is through a device that we've developed called our closed loop FVS sleeve. You can see it on the screen there. This is a wearable fabric sleeve that zips up. And inside that sleeve, there are 70 electrodes. And each of those electrodes can do two different things. So the first, as Lauren alluded to, is we can sense muscle activity. So your muscles generate, there's electrical activity when your muscles are moving. And these electrodes are designed to sense that, which is called electromyography. We call it EMG for short. We then take those signals, we run them through a computer where we're decoding. And for this audience, think of decoding as just classifying. So we're trying to classify to understand what their intended movement is. And then we can activate some of those electrodes, just like what Lauren showed in the video, with functional electrical stimulation. Except now, instead of having these sticky back electrodes that are manually placed, we just have electrodes that span the forearm. So all that happens in software. And when everything's working properly, the user thinks about moving, we sense that, decode that, and stimulate all in a span of 100 milliseconds. And so they think about moving their hand, and then the system assists them with that movement in near real time. So I'm going to walk through a little bit of the process. First, of how we actually decode that motor intent from the electromyography. Talk briefly about some of the biomarkers that we can get out of that EMG data, because it's very rich and has lots of implications for what we might use this technology for going forward. And then lastly, I will kick it back over to Lauren, and she's going to talk about some of the therapies that we've been developing using this technology. So first, how do we decode the motor intent? So I'm going to walk you through some results from our recent paper in the Journal of Neuroengineering and Rehabilitation. So this study, we had 7 able-bodied individuals and 7 individuals with chronic stroke. And each of these people, as you can see in that little illustration there, had the sleeve on their arm, and we're looking at a computer screen that had an animated hand. And the instructions to them are very simple. We just ask them to follow along with the hand on the screen, attempt the movement to the best of your ability, even if you're not able to do that movement by yourself. And so we would have them do this for about 2 or 3 minutes, and we would be recording the EMG data on all 70 electrodes. And then we would be taking that data and combining it with what the hand on the screen was doing. So we had EMG data, and we have the actual movement that we think they're doing. We call those cues. And so you can imagine that gives you a nice training data set for building an algorithm. So on the right-hand side, you can see I pulled out just 2 EMG channels, so you can see what a raw EMG time series looks like. The background colors there, blue is hand close and orange is hand open. And so you can see that top channel has a lot of response on hand open, not so much on hand close, and vice versa for the bottom channel, which is more responsive to hand close and hand open. So that's what we expect to see, that the electrodes that are over certain types of muscles are going to have a lot of activity when those muscles are active, and not so much when they're inactive. But of course, we don't have 2 electrodes, we have 70. And so we can now visualize all 70 electrodes at the same time here in a heat map. And just from like a basic exploratory data analysis perspective, you can see the hand opens, which is the first and the third movements. We see a lot of activity on the higher numbered channels, but we see less activity sort of in the middle channels, like between sort of 20 to 40. Whereas with hand close, we see activity across most of the channels. So it gives us a pretty good sense that we're going to be able to tell these 2 things apart. We can then build an algorithm that's classifying between hand open, hand close, and rest. And then we can go back at the end and say, like, well, what does a typical hand open or hand extension look like? What does a typical hand close or hand flexion look like? And so you can see these heat maps, which are just the average activity that those heat maps there at the bottom, or if you imagine the sleeve sort of laid flat on the table where the wrist is at the top, the elbows at the bottom, the extensor muscles are on the right, and the flexor muscles are on the left. So it just gives you a sense of sort of spatially what's going on with the activity that we're seeing. So to delve into a little bit more detail, some of the principles that go into the data processing and decoding that we do. So first of all, it's imperative for us that the pipeline operates in real time or close enough to real time. In our case, that's about 100 milliseconds duty cycle. So that's important because if we're doing closed loop stimulation and the user is trying to open their hand, if there's a big lag, they're going to feel dissociated from that movement, or they're going to be wondering, like, is this thing working? And so there's a lot of really good evidence that you need to have that lag very, very slight. And we found 100 milliseconds is a good balance between responsiveness, but also giving us enough time to do all the computations and data collection that we need. So also, I mentioned that the user is actually looking at the screen. And so there's actually a lag that we have to deal with where the hand on the screen moves and then the user is moving slightly after that hand on the screen moves. And so that leads to some label uncertainty in our cues. And so that's another challenge that we have to deal with on the data side. A challenge that we're always dealing with, that Lauren's always getting on my case for, is that anytime we're collecting data that we use to train our algorithms, that's time with the patient that's not spent delivering therapy. And so one of our main goals is to try to do all these decoding algorithms with as minimal amount of data as possible. And then lastly, we have a desire for simplicity that's driven by several different requirements. One is the real time. So anything that's just too complicated to run in a 100 millisecond time frame is a no-go for us. Anything that's hard to debug, so a lot of the black box methods become kind of challenging for us to use in the clinic. And then eventually we want to take this device through FDA. So we want to have it be very straightforward for them to understand what we're doing. So this is the typical data flow that we use. So we start off with those raw EMG time series. We run it through a series of filters that are just focusing on the frequency range where we expect to see EMG data and taking out 60 hertz electrical noise. We then partition those time series into 100 millisecond bins, which is how we do our processing. We calculate our features. For this example, we're using the root mean square, which is a standard feature in EMG data processing, but there's lots of different features that you could choose. Standardize the features. Then we deal with that Q shift that I mentioned, and then we train an algorithm. In this case, we're using a neural network decoder. So on the right, you can see what this Q shift looks like. So hopefully you can see my mouse. But the top bar is the actual cue that the user saw on the screen. And then the blue trace is the overall EMG activity. So you can see they're basically at no EMG activity. When they get the cue, a split second later, their EMG activity shoots up as they respond to the cue. They try to hold that pose, and then their EMG activity returns back to zero when the cue goes to rest. And so we've experimented with a couple ways of dealing with this. So you can see here, you can just do a standard, a fixed shift. So you can shift it over by 400 milliseconds or 600 milliseconds, but that doesn't capture what's actually going on. And so we developed this method that we call the dynamic Q shift, where essentially all we're looking for is the sharpest change in slope on these two, on the upward and on the downward. And then we adjust our labels accordingly. And so that gives us a little bit more clarity on making sure that those labels that we're using to train our algorithm actually match the underlying EMG activity that's going on. So lastly, I'll talk a little bit about the way that we do our decoding. We've experimented with lots of different types of classifiers to do this. For this particular paper, we chose a pretty simple neural network decoder. So the decoder is predicting on the current time point plus the 3 most immediate time points behind it. So it's 400 milliseconds of data. And the input there is now 70, which is the number of EMG channels we have, and the 4 historical time points. That goes into a neural network that has 2 fully connected dense layers that use batch norm and ReLU activations. And then this is actually one of the most challenging decoding problems that we have with our stroke participants. So in this experiment, we're having them do 12 different movements plus rest, and we're trying to see how well we can differentiate between those. So here are some of the results with our stroke participants. On the top left, you can see on that A subpanel, those are the raw accuracies with the different Q shifts. The first thing that jumps out, at least jumps out to me, you have a wide range in accuracies among the different participants. And that's expected, and that also corresponds to their level of impairment. So in both stroke and spinal cord injury, we always half jokingly say like no two strokes, no two spinal cord injuries are the same. And that's very true as far as what movements participants can and can't do and what that EMG activity looks like when they're attempting the different movements. So we can calculate accuracy, which is just the standard accuracy you would do in any classification problem where we're looking at the binwise 100 millisecond time point accuracy. You can also see how the accuracy changes if you don't do anything about the Q shifts versus doing a 800 millisecond Q shift versus doing a dynamic Q shift. And the bottom line is doing the dynamic Q shifting does give you a significant boost in accuracy. We can calculate all the standard metrics, confusion matrices. One of the other things that we do is we do a Q-wise metric. So instead of looking at 100 millisecond time bins, we look at it as just, we ask the participant to open their hand. Did the coder decode a hand open for the majority of that Q? And if so, we call that a successful Q, and if not, it's a failure. And then we can calculate the success rate. That tends to be a little bit more aligned with what we observe. So when we ask the user to do it, did they do it or not? Whereas the 100 millisecond time bin is it can be a little bit noisy. And then we can also compare that. So Lauren does an assessment for each one of these movements to say, does this participant able to do that movement with normal range of motion? Is it impaired, or is there no movement? And we see that, as you might expect, for the normal movements, we usually get really high accuracies, and the less function they have, sometimes the accuracies will decrease correspondingly. So I'm going to move on to the movement biomarkers. So biomarkers are really interesting. It's not the primary reason we designed this device, but we're finding that there's lots of use in this, and we think it adds a lot of value.
Steve, can I ask you a question?
Sure.
Can you go back one slide? The vertical bar next on the far right, the success rate and movement score, are those what you were talking about with the movement success versus kind of movement measurement?
Yeah, so the success rate is each participant had 5 cues for each movement, and we're counting out how many of those cues did the decoder predict the right movement for the majority of that cue. So that's what the success rate is. And then the movement score, that is coming from Lauren or whoever the occupational therapist is, who's actually physically evaluating the participant to see how well they can do that movement.
And then it's a scale on the right. So you were very successful on the success rate.
Yeah, so for this participant, they were perfect on most of the movements. They had trouble with thumb abduction and thumb extension, which is essentially separating the thumb away from the rest of the fingers. For the thumb abduction, they had no movement, and for the thumb extension, they had incomplete range of motion, so very little movement. And those were the two where we struggled the most with the decoding. Does that make sense?
Yeah.
Okay. So for the movement biomarkers, there's a couple of reasons why we think this is important. First, eventually we want this to be a device that people can take home and use roughly independently. Maybe they have a spouse or a caregiver that helps them, but without the direct oversight of an occupational therapist like in traditional therapy. And so any of these biomarkers that we can pull out that help us track their progress over time adds a lot of value. It also helps us make the case for why they should be continuing to get therapy if we can show that they're continually improving. And a lot of these biomarkers we found are a little bit more sensitive than what you can just like physically observe in terms of change. Another really important thing that we're thinking about is for both stroke and spinal cord injury, conducting these clinical trials to test these things and get them to market is incredibly expensive. And one of the reasons is because there is a lot of variability in these populations. So any biomarkers that we can use to help with our experimental designs to help stratify patient populations would be incredibly valuable in that regard. So I could probably spend the whole talk talking about the different biomarkers, and there's a lot of cool statistics that go into this, but I'm going to keep it to the one slide for now, and then happy to answer any questions and refer you to a couple of our papers on this topic. But the idea here is what information can we pull out of this EMG data? So we're basically measuring muscle activity across 70 different locations on the forearm. And so 3 biomarkers that we look at very commonly are co-contractions, muscle synergies, and motor units. So to start off, co-contractions in an able-bodied person, when you attempt to, say, open your hand, you're able to very clearly activate those extensor muscles to open the hand, and your flexor muscles, which are for closing your hand, are not activated. Oftentimes after stroke, it's hard for that person to activate the one set of muscles without activating the other. And broadly, when that happens, we call that a co-contraction. And so we can isolate the different muscles in the sleeve data, and then co-contraction index is really just a ratio of those muscles. So we can see which muscles are getting co-activated. And oftentimes, the user is not intending to co-activate, but they can't help it because of their injury. And so that's the co-contraction index. Getting a little bit more sophisticated is muscle synergies. So as a statistician, you can just think about this as I have 70 channels of data over time. I'm going to do a dimension reduction, and I'm going to decompose these signals into, like here we're using non-negative matrix factorization to do the decomposition, and we get these essential units of movement, and they trace over time. And so the interesting thing here is this is not just like a statistical exercise, but this is actually with the non-negative matrix factorization, there's a lot of work that shows that this is actually mimicking what the body is actually doing when we move our body. So we activate different sets of muscles in a coordinated fashion, and those are called muscle synergies. And so we're pulling those muscle synergies out using non-negative matrix factorization. So what we found, and which is consistent with the literature, is that after a stroke, these muscle synergies are similar to someone who's able-bodied, but they are altered in different ways. And especially, as Lauren mentioned, with hemiplegia, where you have one side that's affected and one side that's not, we can actually put a sleeve on both arms, and we can actually look at the differences between the affected and the unaffected arms. And so the muscle synergies give us some insight onto which areas are working, which areas are not working. That helps to inform some of our strategies for where we might want to stimulate. And then it also helps us to track how these synergies are evolving over time as our participants are going through different therapy protocols. So the last one, and the one that I get most excited about, is motor units. So motor units are really the fundamental signal coming from the brain to the muscles that send those movement commands. So these are little electrical impulses. You can see what one looks like there. And if we had perfect recording of the motor units, that would be the purest, cleanest signal for motor activity. Unfortunately for us, there's hundreds, if not thousands, of motor units that are going on all simultaneously, and there's a lot of noise. So this actually becomes very much a very large cocktail party problem. And so similar to like what we would do in a stats class with the cocktail party problem, we use a variant of independent component analysis to try to break apart that EMG signal into distinct motor units. And we've shown that when you get those distinct motor units, your decoding accuracy can go really high because you're getting a very clean signal of motor intent. And then these also become really, really nice biomarkers for tracking progress over time. So the last thing I'll mention that we've done with all these biomarkers is you can collect a few minutes of data with the EMG sleeve, do all these biomarker analyses, and then we throw all the biomarkers together and just do a simple principal component analysis. And what you see on the right there is plotting the first principal component, which here we're calling the combined biomarker signature, and plotting that against the Fugl-Meyer hand subscore. So what's that mean? The Fugl-Meyer hand subscore is the gold standard measurement of hand function after stroke. And so what you can see here is that just with that first principal component on the biomarkers, we get a very accurate, very close tracking of what the Fugl-Meyer hand subscore is. So that's really important because Lauren or one of the OTs might do this assessment, which is a hands-on assessment. It takes them 20 or 30 minutes to do. And so like in our studies, we might do that like once a month because it's time consuming. And so if we can collect a little bit of data with the EMG system, potentially you don't even need the occupational therapist there, and we get a pretty good sense of what their hand score is, that has a lot of value, especially as we think about protocols where people might be taking the system home and they might not have an occupational therapist who's observing all the time. So I'll point you to, there's that Journal of Neural Engineering paper there, and we just had a preprint that came out on the motor units if you have more interest in that, and also happy to answer any questions as they come. So the last piece of this is delivering the therapy. So everything I've talked to date is kind of on the recording and decoding side. But now I'm going to talk a little bit about how we do stimulation. So here we have a trace of a single EMG channel. It looks like what you saw before. But once we start doing the electrical stimulation, the functional electrical stimulation like Lauren showed, we lose a lot of that EMG data. And that's because whenever we turn on the FES is much higher signal than anything that we get on EMG. And in fact, if you just use a standard EMG system and you start hitting that same arm with FES, you have a good chance of damaging your EMG amplifiers. And so at Battelle, we've done a lot of work on the hardware side to try to solve some of this problem. And here's kind of what it looks like if we zoom in. Typically, functional electrical stimulation is delivered anywhere from like the 20 hertz to 50 hertz frequency range. And so what that means is there's a sharp FES pulse, and then we wait for about 50 milliseconds, and then we deliver another FES pulse and another FES pulse. What we've been trying to do with our hardware is design an amplifier that can recover very quickly, because when you hit it with that FES pulse, it just rails the amplifiers. And so we've designed some hardware that can recover after about 20 milliseconds, which when we're stimulating at 20 hertz, that means that we're getting about 30 milliseconds of good EMG activity in between our stimulation pulses. And so this is what that actually looks like with a couple, about 100 milliseconds of data here. So the black is what we're actually recording off the electrodes. You can see as soon as the stim turns on in that red area, it rides up to the rails, and then it has this recovery period. But then that blue activity in between is good EMG activity. We can then decode that EMG activity. And again, we're using a root mean square kind of feature, which is essentially an average. So we're averaging over that 100 millisecond time bin. We're just losing some of the data, but we still get good EMG activity. And we can use that to then control the FES, not just the onset of a movement, but we can actually decode when the user is attempting to stop the movement or when they're trying to switch from one movement to another. And so that really changes the idea of what we're doing from what you saw in that video, where there are these beeps and there's these like strictly timed kind of functional electrical stimulation, to what we call volitional control. And that means that the user is in complete control of the FES, turning it on, turning it off, and switching. And so we think that is really going to drive neuroplasticity, which is what we're hoping to see, which is the motor system adapting and improving over time. So this is what the hardware looks like. And then you'll see on the right-hand side, this is what the data from the system looks like. It looks very, very similar to what you saw with the EMG. The difference here is now every time we're decoding a movement, we're also triggering the FES for that corresponding movement. And so again, when the user is thinking about the movement and the system is working properly, they think about opening their hand, whether or not they can open their hand. And then the system will kick in and give them stimulation to help them open their hand and complete that movement. And then it also is monitoring them as their hand is open, and figures out when they're stopping and returns them to rest or switches to a different movement. So that was a lot of words. I'm going to show a couple videos here. So this is one of our participants who has a spinal cord injury. So on the top, you can see him attempting, his goal is to lift that paperweight and put it from the white area onto the black area. It's a little bit hard to see. That black area is about 3 inches raised off the table. And on the bottom video, he's actually using the system. And you can see he's able to pick up that paperweight and move it with pretty good speed. On the bottom, you can see the heat map, which is showing the EMG activity in real time as he's doing that activity. And then when you see those red and blue dots light up, those are the electrodes that are delivering stimulation. So red is anode and blue is cathode. So you can see the stimulation that he's getting. And then lastly, on the bottom left, you can see the actual decoder outputs in real time. All right, I'm going to hand it back over to Lauren to talk about some of our recent results in stroke.
Yeah, so we did a very small pilot study, just more of a feasibility study in 2 adult stroke patients with what we call chronic hemiparesis, meaning that they're some literature defines it differently. It's either 6 months or a year post stroke. So they're not really in that like early spontaneous recovery phase after a stroke where there's oftentimes rapid recovery. And the reason that we chose chronic stroke for this is for the reason that we wanted to be able to show that this wasn't just spontaneous recovery, that the system was actually doing something And so both of the participants in this study were pretty significantly chronic stroke. So one was 5 years post-stroke and one was 7 years post-stroke. One was an 84-year-old male. He was right hand dominant, and the hemiparesis, or his impaired side, was his left side. So it was his non-dominant hand. And then the other was a 64-year-old female who was 7 years post-stroke, right hand dominant and right hemiparesis. So her dominant hand was her impaired hand. And if you are interested in the results or any of the methods that we use for that, the paper citation is listed here at the bottom for this case series. And so what you can see here is this was very early on when we were developing the system, but the participant is able to use that closed loop volitional control. So when she's attempting to pick up the object, the system is detecting that and then closing her hand, and then same thing opening. I think Dave mentioned this. In stroke, it's actually harder for patients oftentimes to open their hand than it is to close it. And so there's a lot of value in even just being able to like release objects and open. And so we spend a lot of time practicing that. And so you can see here, she's grasping the bottle. She's able to rotate and pour. And at the bottom, same, you can see the heat map of her EMG and then when the stimulation turns on and off. And then these were the results. So we did 8 weeks of therapy 3 times a week, so 24 sessions for each of them. And then we followed them for an additional about 10 weeks after they were done. And it was really interesting what we found. So both of them made improvements above what we call the MCID, or the minimally clinically important difference score, for 2 very commonly used outcome measures in stroke. One is the action research arm test, which has patients grasp and release objects like large blocks, small blocks, pick up marbles, different things like dexterous movements and gross movements that you do with your hand and arm. And then the UEFM is the upper extremity Fugl-Meyer. And that one's looking at more what we call synergies. So how well the whole upper extremity works together. So you're going to capture more like spasticity or a hand tightness, things like that. And how coordinated their movement is going to show up a little bit more in that one. So if we look first at the graph on the left, blue is participant A, orange is participant B. Both of them made pretty significant improvement early on. And by 8 weeks, both of them had surpassed the MCID, which is 5.7 points, which is pretty significant, especially considering that they were 5 and 7 years post-stroke. But what we found most interesting was that not only were their results maintained, in some cases they were actually exceeded. And you see that again over here in the Fugl-Meyer. So Fugl-Meyer, they jumped up pretty early on, and they continued to increase and stayed pretty consistent. They dropped just a little bit. But what we found when talking to them about why this might be was that they were both saying things like one of our participants, 6 weeks after the study was over, was saying, I tied my shoes for the first time in 7 years the other day, which is a bilateral task. It requires both hands. And oftentimes patients just they have what's called learned non-use, where they don't use their impaired hand anymore. And so they would just kind of adapt and try to do it one-handed. But he was spontaneously tying his shoes. Same thing with the other participant. She said that she was cooking and she found herself cutting vegetables spontaneously, like didn't think about it. Whereas these are patients that any type of movement, when you have a stroke, it takes a lot of thought and a lot of really targeted, okay, I'm going to move my hand over here. It's not spontaneous in the way that we normally move. And so what we think happens is, because it's this closed loop pairing, we're tightly pairing the motor and the sensory feedback together. They're getting that true volitional sense of control that even when they don't have the sleeve on, they've relearned how to do those tasks. So they were more motivated to use their hand and continue using their hand beyond therapy. And so this is just one example. This is participant 2. She, again, is 6 years after stroke, had what we consider moderate impairment. So not terrible, not the worst we've ever seen, but not minimal. And what she's trying to do, this is a very, very dexterous task. She's trying to pick up a ball bearing with her ring and her ring finger and her thumb. And after 1 minute, she's unable to do the task. It'll just go. And then after the 8-week intervention, this is her video attempting the same task. So did it in about 6 seconds. So we get pretty excited about the small things, as you can see, but they're really big things. And what's cool about this task is we weren't training to this task specifically. We weren't explicitly practicing every day, picking up a ball bearing with the ring and thumb. But this person, she got used to using her hand and using it voluntarily. And so that lent itself to these more like dexterous movements that she couldn't do. This is the same person who said that she was able to spontaneously cut vegetables. And so this just illustrates how there's a lot of carryover into that volitional control and tightened motor and sensory feedback. And that concludes the presentation portion. We do want to acknowledge our collaborators and funding sources, which are all listed here. And we would be happy to open it up to questions if anyone has any.
I can start with a couple questions here. The first one is for Dave. You mentioned time and training is, so you already answered that one. So you talked about decoding the signal with the neural network. Can you share a bit more about how the neural network is training, considering historical data like your 7 and 7 study, and then trained again for individual patients?
Yeah, so to start, we would be basically every day we would be starting fresh. So the participant would come in, we would collect like a block of data, we would train a model, and then we would have them use that model, and we would typically go through a cycle where we would collect a little training data, update the model, collect a little bit more data, update the model, collect a little bit more data, and it was tedious to just say it. Right? And then eventually we reach a point where either we say, all right, we've spent enough time, we're gonna move on, or hopefully we reach a point where we say, okay, the performance is good enough, let's move on. What we've started doing more recently, and the neural networks enable this, but we've also done this with some ensemble tree methods, is trying to pre-train some of these decoders. And so for one of our current studies, we have spinal cord injury participants who are coming in and they do about 42 sessions with us over the course of 3 months. And so we have a lot of historical data with them. And what we found is that that sleeve has to get placed on their arm every single day. And so the placement might be a little bit different from day to day. Their arm might be a little bit different from day to day if there's humidity, or if they took a shower right beforehand, or also a lot of these participants, especially the spinal cord injury participants, they get muscle growth throughout using throughout the study because they aren't using those muscles usually when they come to us. And then we're forcing them to practice a lot, and so their arms often will get, the muscles will get bigger. But we found that with a couple of days of historical data, we're able to get pretty good performance by pre-training some models, and then either just using them or just having like a really short, like minute-long calibration period, and then we go. And so that's going to be really key as we try to move this forward, because the setup process we know is one of the big barriers to adoption. The other thing that we've been working on that's pretty exciting, don't have any results to share yet, but we've been thinking also about, as they're using the system, we collect a lot of data where we don't have labels. So like, for instance, we'll do like a typical task we might do with them is playing a card game or playing checkers. And so we don't have those tightly timed labels with the EMG activity, but we can infer what those labels are, and then we can try to use some unsupervised methods and clustering to try to update our decoders, even though we don't have that like very clean textbook labeled data. And so we have some techniques and some ideas around how to do that we're testing as well.
Okay, this one's a really tough one. So what kind of assistive device is next? Could this kind of technology be used as like a whole body suit to let a quadriplegic person use all of their body?
Can I take that one?
Sure.
So,
sure. So we actually are working on a lower extremity sleeve right now as well. I shouldn't say we're working on it. It's developed. It's just in testing right now. Ultimately, it would be awesome to have a full body suit. Right now, we do one arm at a time, but I think that honestly, a logical next step, especially with quadriplegia, might be to be able to put 2 sleeves on someone and see if they could use their bilateral. Because most of the tasks that we do in our everyday life, even if it's not really thinking about it, if I go to grab this cup and then I pull the lid off, like I'm using both hands. no matter what we do. And so giving people back the ability to use both hands, I think, is a really good starting point. And if you look at the literature, especially with spinal cord injury, we oftentimes think that the number one priority for spinal cord injury patients is going to be walking. But what we've found is that if for anyone with quadriplegia, so involving upper and lower extremity, the upper extremity is always the number one priority, getting back your hand function, because you can live a very independent life as a paraplegic if you could use your hands. And so I think that the logical next step would be try to get a home system or something like Dave said that's more streamlined to be able to do one limb, and then work on trying to do both. We get patients all the time that's kind of do both arms at the same time. That would be awesome. And then we also in parallel are doing like leg sleeve testing. So a bodysuit would be awesome. I don't know if it's going to happen in the next year or so, but hopefully somewhere down the road.
That's okay. Keep on it. Okay, I don't have any other questions, so I guess we'll wrap up by thanking you very much for this talk today. It's amazing work. You know, I know any patients that have the opportunity to interact with this have to be so excited about the additional possibilities it's introducing for them. So thank you for this work, and thank you for telling us about it today.
Of course, thank you for inviting us.
Thank you.
Happy to be here.
Bye.
Bye.